experiment, the Fleisch-and-Pons experiment, fits in overall in the context of science, concern, physics, making physics. Some history, early on, experiments didn't get positive results. There were a lot of arguments as to why it was impossible. There are positive results. The positive results motivate us to be interested in it and to try to understand a little bit about the experiment, what the experiment means, what it's doing, what's happening in the experiment. And we started that yesterday discussing some more conventional topics, lattice expansion, the issue about chemical potential, phase diagram, hard to load at higher loading, and the tool measure loading at the resistance ratio. So today, I'm interested, I want to continue the discussion. We'll be talking some about electrochemistry, some about loading, some about hydrogen and metals, vacancies, and, well, there's a lot of material. I want to begin talking about electrochemical modeling. Electrochemistry is tough. Molecules are complicated, surfaces are a mess, catalysis is not an easy thing to do, to describe, and if you like, the electrochemical models I'll be talking about briefly here are, well, they're important. There's some of the big success stories in electrochemistry, and as such, they're in textbooks. The mechanisms I'm going to be talking about in the literature called hydrogen evolution and deuterium evolution reactions, HER, DER. And there's quite a bit of literature. These models apply to a wide variety of metals. And in many cases, they work. As we're going to find out, on the face of it, they seem not to work for Fleisch-and-Pons experiment, which is one of the reasons we're interested. So we're going to begin with loading hydrogen and deuterium into palladium. And the reaction mechanism that is responsible for this is the Volmer reaction. We have Volmer over here. We have D2O coming in. At the surface, deuterium atom is deposited onto the surface of the metal, and OD minus comes off. So if you like, there's an exchange, deuterium atom one way, electron the other way, which will be important in terms of the modeling. This is actually more significant than just the pretty picture. The idea is that because there's an electron being exchanged, the process is connected with the electrochemical current. If you look up a battery voltage or a current source, and you drive the current, if you like, it forces this reaction, which forces hydrogen or deuterium onto the surface of the cathode. That's interesting. It's neat that you can do that. And once you get your hydrogen in, deuterium in, well, it can come out. And how does it come out? Well, the way it comes out is within these models is you have deuterium or hydrogen on the surface, and if they come together, they form a molecule, and the molecule can go off. And I have it here going away from the surface. The idea is it ends up bubbling out. Some solubility, some small solubility in the electrolyte, but it comes out in gas phase. Finally, there's actually four mechanisms in the hydrogen deuterium, the DER, HER family of reactions. The deloading mechanism is, in this case, the Hagelstein mechanism. And it's sort of like Volmer in that D2O comes to the surface, and this time instead of dropping off a D, D is collected, coming off as gas, and then OD minus comes out. And this reaction, I like to think about these things in a bonehead way. If I go back to Volmer, Volmer is a little bit like Santa Claus. If loading is good, Volmer comes in, breaks brings in deuterium presence to leave at the cathode. So Volmer's good. And if I think of Hairovsky sort of in the same sense, Hairovsky's like the cringe. So Hairovsky, you turn on current, D2O comes in, but instead of leaving hydrogen or deuterium on the surface, it's taking it away. And so as a result, this is a reaction that would cause decreased loading when the loading is high. So there's a fourth mechanism which goes from when the Volmer reaction leaves hydrogen and deuterium on the surface, it's adsorbed, instead of going adsorbed to absorbed, which means it goes from the surface to the interior. So that's part of it. In this case, the reactions, the processes are pretty nearly steady state, so I'm not going to worry about the details of how it goes back and forth. Now, for the Volmer reaction, the general, having specified the reaction, we pretty much have everything we need in order to model it. And the electrochemists have put together a ridiculously efficient way to model these reactions once you've got some idea of what's going on. And I'd like to find here's the formula for it. And I'm expecting that you're looking at this and thinking, oh, there's a bunch of terms and equations and it doesn't make any sense and it's all great. So we'll go on and we'll suffer through this. However, there's some reason and rhyme logic to it. As an applied physics type, you stare at it, the first thing you look at are these exponential terms. The exponential terms, this one came about from the chemical potential of the electron. Electrons being exchanged. And you care about what the chemical potential of the electron is. This one came about from the chemical potential of the hydrogen or deuterium. In this case, we're going to have this one go away. On the other hand, if you have the inverse Volmer, normally Volmer drops hydrogen off, which is what this term is doing. But if have the inverse process, hydrogen is going the other way, then you get this term. And if the delta goes to zero, you get a 1 here, and you get the full term. So this is, of course, on the chemical potential of hydrogen and deuterium. So the more hydrogen and deuterium you have, then this term means the more it wants to go away. Now, if you're dropping hydrogen off, you want there to be sites where you can put the hydrogen or deuterium. So this is the beta is the fractional loading. So 1 minus the fractional loading tells you roughly how many sites are available to drop something off. And there we have it. The roughness factor parameter, which tells you basically how strong things are. If you've got the form of the equation like this, you can actually fit to experiment. You can start to do some physics or electrochemistry. In the model, there's something called a Frumkin parameter. See, Frumkin parameter. What the heck is a Frumkin parameter? Well, Frumkin was a famous electrochemist. And the basic idea in connection with this is that if you look at the chemical potential for hydrogen, in this case deuterium, above the miscibility gap near room temperature, it's roughly linear. And Frumkin said, well, if it's linear, then when I can simplify my equations, then I can make things work. So, for example, implicit in this equation, for example, is linearity with the chemical potentials linear loading above the miscibility gap here. So that's sort of what's in this model. Now, if you've got some data, like you've got current density over all kinds of orders of magnitude, so milliamp per square centimeter, amp per square centimeter, and this is the overpotential associated with the kappa. So if you plot the overpotential as a function of current density, then you go back to the Volmer equation. You see the overpotential showing up as part of the chemical potential for the electrons. And turns out you can fit the data to your expression. And when you do, you get a number for the strength of the Volmer reaction and Volmer current parameter. So if you like, that's sort of the process to take advantage of these equations and to make them work. And once you do that, you end up with the model that can do something. In the case of the Tafel current, you say, current, what's the current? I mean, it's hydrogen and deuterium coming off the surface and making gas. But we think of it as equivalent hydrogen current, and you can use the equations sort of on the same footing with other equations. But this sort of works the same way. This is the one that makes the gas, and it takes 2 hydrogen and deuterium atoms, so there's a vector 2 here. And this is the Frumkin thing, which is linear in the chemical potential. And this is the coverage squared, which means you have to have 2 hydrogen and deuterium to make a molecule come off. That's sort of how this thing works. Now, there's one called the Volmer-Tafel regime. The Volmer-Tafel regime is sort of the simplest way things can work. If the Volmer reaction brings hydrogen to the surface and goes off as gas, then in equilibrium, in steady state actually, they have to balance. The hydrogen coming in matches the hydrogen going out into gas. So here's the hydrogen going out in gas, here's the hydrogen coming in for the Volmer reaction, and you set them equal to one another, and you get an expression. And this thing's called an isotherm. So the idea is that loading's on this side, and the overpotential's on this side. So if you move your overpotential up or down, you look over here and you calculate what the loading response is. So you get an isotherm that you can connect with the experiment. So here's one that I've connected with the experiment. So I had some data from Green and Briggs, some very good electric chemists that published data very relevant to these kind of models. So here's overpotential, here's loading, and here's the dots for the experimental points. Here's the line for the Volmer-Tafel isotherm, and at low loading, that's called at low current density, which corresponds to low loading. In this case, that's called the Volmer-Tafel region because Volmer-Tafel mechanisms are what dominates what's going on. So in the Volmer-Tafel regime, you can actually match the curve against the data. And to do that, this is the parameter associated with Tafel, which sort of tells you how fast the gas is coming out. This is a roughness factor that Briggs and Green figured out from their experiment. So if you like, I now have all the parameters to make my model work, so I can sort of figure out how things go and how things come out in life. So if I stare at this, here's data for 10 molar lithium deuteroxide, 1 molar lithium deuteroxide. Curves are slightly separate. I stared at these for a while. I thought, that means the more salt that you have in the electrolyte, then the higher the loading could be. So worked and worked and worked to try to get the models to reflect that. I had to do gymnastics and so forth. And at some point, it became so difficult, and the assumptions started to be so strange that at some point I emailed Briggs and I said, is this significant? Please put it, no, that's not significant. But the minor change here is not something that can be deduced as relating to the salt, molality of the salt. Okay, now I'm going to come back to the cold fusion experiments. So yesterday we had some data points for some negative experiments, so some things that didn't work. At MIT, for their heavy water experiment, they got a loading of 0.75. For the light water, they got a loading of about 0.78. The CalTech negative experiments, they reported loadings between 0.77 and 0.80. And we'd argued that those loadings were too low to make things work. And we'll argue that some more today. But before going on, let's see how this compares with Green and Briggs. So here's Green and Briggs. The current densities in the CalTech experiment were sort of in the they were sort of in the neighborhood, a little bit under 100 milliamps, as I recall. So somewhere near 100 milliamps, this is a little bit over 0.78. This is a little bit under 0.82. You look at the grain and Brits data, you look at the MIT and CalTech data, and you conclude that, well, MIT didn't really achieve a loading as good as grain and Brits. Grain and Brits are good electrochemists. Hydrogen and deuterium electrochemistry really wasn't the area of expertise of the MIT team. Nate Lewis and the CalTech folks did a bit better, so these guys largely consistent with Green and Brits level of loading. So the takeaway message: hydrogen evolution reaction model, big advance over years and years ago in electrochemistry. It actually does seem to give a basic picture for how the loading works. You can match the equations against experiment. H and T is peroxide cathode by the current. H and T in the Volmer-Tafel region leaves cathode in the gas formation. Textbook model is a big success story, and we have a way systematically to match the parameters of experiment and get a message. Takeaway message is something. That's why I brought that. Entertain questions. Questions or thoughts or comments?
Does the migration of H or D into the metal off the surface affect these relationships?
In principle, yes and no. If you're doing an experiment over a very long time scale, and you're in steady state, and when you're steady state, then the diffusion's already happened, and the loading's flat and set together. If you're doing it transiently, then you're going to have very non-uniform loading. So the basic idea is you'd like to solve these equations together with a diffusion model, the absorption model together with descriptions. When people do that, they compare against very fast transient kilohertz, 100 hertz to kilohertz range experiments. You can learn a lot about what's going on the surface when comparing models.
Yeah. Being an engineer, I guess I want to know what's the best way to measure the loading? Is it school resistance?
You're asking about a value judgment, and what is commonly done, sort of because it's easiest, is to do the resistance ratio, which we discussed yesterday had the difficulty that it's an integral measurement. So you have a very long time experiment, steady state conditions, and we use the resistance ratio to be a very effective combination. On the other hand, if your experiments are transient, use resistance ratio, who knows what.
There were 2 points where the resistance.
Right.
So you're looking basically for that second point.
We'll talk about that. Yeah.
Okay.
Okay. Excess power versus loading. Need for high loading. So Fleischmann argued from day one that you needed high loading. He argued it in a little bit obscure fashion, but that was the point of his argument. There were these discussions that Nate Lewis, no effect, and a fellow from Stanford, I think it was Bob Huggins, would say, I wasn't there, so I read it right up, but he said, well, you're loading something high enough. Nate Lewis said, well, loading's plenty high, there's just no effect. So let's think a little bit about the loading. So in one of the early experiments at SRI, some data was taken where some excess power was observed. And associated time correlated with the excess power was the loading ratio on this axis. And if you like, when the excess power was low, the loading wasn't quite as high. When the excess power was higher, when the excess power was higher, the loading was higher. Also, there's a correlation between loading and excess power level. And so the data points for that experiment is plotted. You get a curve look at something like this, which suggests that you don't get excess power until your loading reaches some threshold value. There's questions to what the threshold value is. In this experiment, looks like it's 0.85. Other experiments, a little bit less. And some experiments a little bit larger. But a number of experiments seem to have some agreement that there's a threshold in loading before you can see excess. Here's some data by Kunimatsu, this ICCF3. Same time the SRI team presented their data, they didn't know these guys are taking data. The results were very similar. So here's 0.85. So Kunimatsu is seeing excess power with a threshold that's a little bit lower than the SRI, but it's sort of the same basic effects appearing. The takeaway in this is that Fleischmann argued that we needed high D to PD loading, and in a large number of experiments there seems to be a correlation between loading and excess power. Thoughts, comments, questions? So now let's revisit the electrochemical model. And the issue is the following. If you have to get high loading, we go back to Green and Brits. According to Green and Brits, your loading of your average cathode is sort of going up here. It's kind of, you can see that it's sort of turning around, and if you take it even the higher current density, it goes up and starts to come back down again, as we'll show. So the question is, what do you have to do to get your loading up? If the threshold's 0.85, these cathodes aren't making it to 0.85. So start to think, well, if Briggs is arguing with the difference between these two cathodes, has something to do with the cathodes. It's property of the cathodes. Maybe what that means is I have to start sorting through cathodes. Try one, try another until I can get this curve to start bumping up. But I'm scratching my head and thinking about it. I think, there's got to be some reason for that. I mean, it can't be mysterious. If it's like this, that you just have to sort through cathodes so you find something. It sounds a little bit more like either art or witchcraft rather than science. And there ought to be some obvious reason as to why these different curves are showing up. Here's another result. This is data from Akita et al. And you can see this is current in milliamps per square centimeter. So here's 100 milliamps per square centimeter, which is sort of where the Green Brits data ended. Here's the amp per square centimeter. So in the experiments, oftentimes the current starts to come back down. You look how high it gets. Well, this is getting up to something in the neighborhood of 0.84 or so. On the order of what it is that the Green Brits cathodes.
I'm a little confused about the effect of current on loading. It seems that it would take place over time, but there's no time implied by this chart.
The thought here is that this is steady state operation relative to the size of the cathode.
Okay, so it may take a long time to get there.
Yeah.
But after it loads fully, that's what you get.
Right. Okay, so once again we get consistency. This is sort of just like Green and Brits, maybe a little bit better, but we're not getting into the promised land of the very high loading ratios we seem to think. On the other hand, some cathodes do. What I wanted to do is I wanted to show you this data. This is middling early. At SRI, they spent a huge amount of time studying the loading of the cathodes. And so some of those studies continue in different labs even today. So this curve right here is the loading ratio. And I believe this curve is the current density. And I don't know if it's, current density amps per square centimeter, so it's going up to once. They're stepping it up. So the way to read this is the resistance ratio starts out, resistance ratio should start out somewhere near 1. But I guess where it goes from 1 up to this point is not part of the data set. So you see that the resistance ratio goes up to 2. So if we recall that 2 was somewhere near a loading of 0.65 to 0.7 is the curve. So here 2 is, I stand corrected, it's around 0.76 or so. So you're loading, you've got over the hub, and you're coming back down. So you're going back down the resistance ratio curve. And by the time you get down to this point, you get to a resistance ratio that's sort of around 1.6 or so. And if I look at 1.6, I go down here and I'm at 0.93. So here's some, if you like, a relatively early data showing a cathode that's reaching these heroic loadings. So we have examples, and there's lots more examples of loading runs that do get very high loadings. Here's one done with Superwaves. The argument is that the Superwaves have this very complicated structure. I was trying to argue that it's a little bit like taking a drawer that was stuck, rattling it to try to get it to open. Well, in this case, for notorious cathodes, they can achieve very high loading. So what we're looking at here, here's the resistance ratio here. So the resistance ratio is coming down, going way down. Here's the resistance ratio hitting a little bit north of 1.3. And here's the loading on that axis up here that you can see. So this cathode is loading up to 0.97, 0.98 or so even higher. And so here you've got some examples of cathodes that are loading heroically. Now, given these cathodes are loading heroically, what about green and grits? What about this hydrogen evolution model? What about the textbooks? Question is, how can a loading be so high? Why is it so high? What's going on? What is it that SRI did, or what is it that Victoria did? What is it that the energetics guys did to get such high loading? So go back and scratch our head. And in the Volmer-Tafel region, things are really simple. Volmer loads. You got current density, you got loading, and you know how much loading you've got. Tafel deloads, just making gas. And in the Volmer-Tafel region, it's just a balance between these, and everything else, if you like, ends up making the loading even worse at higher current density. So how in the world are we getting higher than 24? That's the question on the table. Mainly, is there some new electrochemistry, some new physics, or the cathode's magic or something? So let's go back to the Volmer-Tafel model. In a sense, the problem has to be here. We argued that Volmer bring the hydrogen and deuterium to the surface, balanced by Tafel gas formation. To some degree, equating these things to getting an isotherm. If you like, one of them's broke. Two possibilities. Pick one. Is it Volmer bringing the hydrogen to the surface, or is it that gas coming out?
Yes.
Which is not described correctly. So the thinking, to think about it, sort of, Volmer's pretty simple. So, if independent of what the innards of the cathode looks like, it seems like Volmer ought to be bringing deuterium and hydrogen from the surface, sort of one atom per electron, pretty much the same. So maybe there's some details about the surface structure and the roughness factor, relatively small factors, but I'm of the opinion that Volmer probably isn't the problem we've got. I'm thinking it might have to do with Tafel. And the idea is that the question is what's the surface? So, for example, in the idealized picture of the hydrogen evolution reaction, the outer surface is where the gas comes in. But on the other hand, if I now generalize my picture and say that what's going on in this cathode is that there's a lot of tiny fractures and voids and fissures and internal surfaces, I can have a large amount of internal surface, and if the gas is coming out, leaking out from the internal surfaces and making it out through cracks and fissures, then it would increase the Volmer-Tafel well beyond what this simple model is including. So I'm going to propose that the cathodes, which are heroic, have on internal links. See if I can make some sense out of that, and then go back and check with the experiment. And the question is
Internal leaks?
internal links.
Correct.
Correct. Oh.
Well,
Fissures.
internal surfaces, and then pathways from the internal surfaces out. So let me think a little bit about it. So first thing I do is I get on the phone and I call my friend Mike McCouvery. I say, well, I have this idea about this hypothetical best cathode. Can you tell me what, in your experience and the energetics experience and Victoria's experience, what's the best cathode you've ever had? What did it do? And the argument was that we got to loading sort of in this range between, say, 0.94 or so at just a few milliamps of current density, which, if you like, is like unheard of. Comparing that to Green and Grids, which is, it's just not even on the same plot in terms of how well it's working. So what I'm going to do is I'm going to propose that this hypothetical best cathode sort of goes through a point, but otherwise has a current versus loading curve. If you like, if you're in the linear regime where the chemical potential is linear in loading, then you get exponential Tafel current as a function of loading, so you get sort of straight lines, linear log scale here. Now, if the internal surfaces, there's 10 times as much as there is external surfaces, then you have this curve. If there's 100, you have this curve, you have